We'll do one more last example in this module that concerns sending random processes through linear systems. And here's the transfer function of our linear system in this case. It is stable. Here's the input to that system, a random process composed of two noise sources. A is just a uniform constant. Well, it's a constant that's drawn from a uniform distribution between 0 and 1. Then this N is unity white Gaussian noise. Our job is to find the mean square, and the variance of the output, and then do it for specific times, a tenth of a second, and then as time goes to infinity. And because it is a stable system with bounded inputs, we would expect as time goes to infinity that it'll actually reach some kind of constants, that these things, these mean square, and variance will reach some constant level. So let's see what happens. How do we deal with such a compound input? Linearity to the rescue. Remember what linearity means. If your input is a linear combination of functions, the output is the same linear combination of the outputs to those individual inputs, so that we can break up, here's our formula for what an output is. We've got the system weighting function, which is going to come from the transfer function, and a sum of two inputs. But we can break that up into two integrals. In effect, we have an output due to the first input and an output due to the second input. And we just analyze them separately. And once we want the total output, we just add those two things up. So let's look at that first guy. The first input was just this A, which had a uniform distribution. What's the expected value of that thing? Well, it goes from 0 to 1. Here's that mean. And we can get the weighting function from a Laplace table. We take the inverse Laplace transform of this guy, our given transfer function, and it is this thing. So we had a formula for the mean of the output. It's the mean of the input times this little integral. Well, the mean of the input is that half, and this integral is the integral of this weighting function. So you take that integral, here's what you autocorrelation function of the input is this thing. Multiply the two inputs together, which means it's a squared, the expected value of a squared. And that is that same uniform distribution. It's third. Let's see. Do you need that? Let's see. We had a formula for the mean square. It was, what was it? G. Oh yeah, that's why we need this. We need this autocorrelation function because it's part of this formula. It's the weighting function with the argument of u and the weighting function with the argument of v times this autocorrelation function, the input. We just discussed this formula in previous videos. So the rest of this is taking the integrals. I'm not going to go through that. So here is the mean square due to that first input. Alternatively, you can recognize that X1 could be analyzed as a deterministic signal. That A, that uniform distributed thing, was like a constant input, but a random constant input. Once you get past time zero, it's just a constant. And by the way, I should have said all this input, all the inputs, they start at time zero. So that the output in the Laplace domain is the product of the transfer function and an input. The input is just a constant, so its Laplace transform is some constant over S. Which gives you that output is just this, and what is A? Well, when you take the expected values of the X and the X squared, you end up just taking the expected values of A and A squared times this thing. Anyway, you get the same answers as on the previous chart, but it's kind of a different way to think about it. It's kind of different because after time zero, there's no more randomness. The only randomness, at least due to this input, came right at time zero. Random of how big of a little jolt that was at time zero. Now we'll look at the other input, which was unity white noise. Its mean was 0. And its mean square, we got that from a previous example. All that arithmetic is down here. I don't want to go through that again because we did it about 2 or 3 videos ago. But we had all that already because we already looked at what happens when you send white noise through a first-order system, which is the situation in this case. So now we have our two outputs. The total output is just their sum. So their mean is the sum of the means, which gives us this. Go back and look what they are. Yeah, the mean of x2 is just 0. So the mean of x1. For the mean square, we do have to take the square of the sum, but this middle term here, because the mean of the second output was 0, you just get the sum of the 2 squared means, which is this. If you go back in the previous charts and look at them. And then the variance is just the mean square minus the square of the mean. So we have to do that bit of arithmetic. There's what the variance is. And then we were supposed to evaluate it at 2 different times. One was at 1/10 of a second. Get these numbers. Pretty small variance. Pretty small mean. And then as time goes to infinity, they go to constants. Here are their numbers, but only because at a particular time. Prior to time equals infinity, it's some function of time. But out as time goes to infinity, they just asymptotically reach constants, and you'll see these numbers are quite a bit bigger than these. So it starts out small and kind of exponentially grows with these kind of exponential functions. And that is it for this module, which is all about sending random processes to linear systems. Next, I think we get to state space, quantization. That should be fun.